Okay, hello, welcome back. Um, in the previous video, I explained that having a linear relationship would help to calculate the expected value of a new random variable, right? So, but the main point here is we need a special condition that the transformation from the original one to the new one must be linear, defined in this way mathematically, right? So today I'm going to give you another example to study the role of the linear relationship assumption. So here I will compare what happens when you have a linear relationship and when you don't. Okay, so this is another example we are going to consider for now. So I have a son, 7 years old now, and we've never been to Disney World yet. So I maybe in a year or two we may have a trip there. I hope so soon as possible. But anyhow, so let's think about the probability distribution. This year, say, in the academic year of 2023 and 2024, how many times can we go to Disney World? 50%, I think zero, maybe. And 40%, maybe once, sometime. But if something special happens, and then we may go there twice for some reason. So it is just my probability distribution of the likelihood of going to Disney World and how many times I go to Disney World. So here, first then, it is a simple exercise for you. I will denote the number of trips to Disney World as x. X is a random variable defined as number of trips. And then can you calculate the expected value of x based on this? Okay. Simple algebra. Pause the video and finish the algebra first. And if you how you do it, the answer so the idea is to have a weighted outcome column. Create another column, and in the column we fill the number by multiplying the outcome number of trips to the probability. So like this. So 0 times 0.5, 0. 1 times 0.4, 0.4. 2 times 0.1, 0.2. So these are probability weighted outcomes. And sum them, then the expected value is 0.6 on average. I expect we are going to go to Disney World expectedly 0.6 times, right? Okay, so this is a simple exercise. And now, but what matters more is not just number of trips, but the budget, right? So to simplify the problem, I'm just assuming that the cost is $1,000. Like each trip will cost me $1,000, or just say admission for our family would be $1,000. Simply assume that, and I will define another random variable y. X was the number of trips, but y is now the total expenditure, total spending to go to Disney World, right? So assuming that the cost of a trip is $1,000, so I would like to save money for this trip for Disney World. Okay, then how can you calculate the expected spending on Disney World trip? So you know the probability of number of trips, and you know the cost of trip, cost per trip. So you have all the information you need. Okay. Okay, let me show you the answer. Here, there are two different ways to answer this question. First, we already calculated the number of expected number of trips, which was 0.6. So you may use that information if you believe the relationship is linear. So the relationship between the number of trips and the total spending is linear, then you can utilize the information about the number of trips. But more safe way is, without any assumption, you can just make another distribution, probability distribution table for the new random variable, and then make another column for weighted outcome, and then just follow the same way to calculate the expected value. So let me show you the first one. What you need to do first is to check if the relationship is linear, and in this case it's pretty obvious because the spending y is simply 1,000 times x. For each trip you spend $1,000, right? So it is linear. It is like from the original random variable, you multiply 1,000 and add 0, right? So it's composed only of multiplication and addition, so it's linear. So yes, the relationship is linear, and then once you realize it's linear, you can simply replace the original random variable with its expectation, and then the result will be the expected value of the transformed new random variable. So the answer is $600, which is intuitive, right? So I expect to go there 0.6 times, and each trip costs $1,000. Then the expected spending would be $600, 0.6 times 1,000. That's how we calculate this. But again, this applies only when the relationship is linear. So if you don't know when it's linear, when it's not, then I don't recommend this way. So in other words, if you understand the linear, what is a linear relationship, then it saves a lot of time. Alternatively, more fundamental way to handle this problem is just do everything by yourself. So original variable is x. I transform x into y by multiplying 1,000, which is simple. And the probability distribution does not change. Probability distribution goes like this, as same as the original random variable. So 50%, I'm not going there, so I'm not going to spend any money. 40%, I will go there once, so I will spend $1,000. With 10%, I may go there twice, so I will spend $2,000. This is the probability distribution for the new random variable. And then you multiply the outcome for the new random variable and its probability to obtain probability weighted outcome for the new random variable. So 0 times 0.5, 0, 1,000 times 0.4, 400, 2,000 times 0.1, 200. So add all the numbers, add all these three numbers. So then the answer is 600, right? As they should be, this is the same as this number, of course, right? Because the relationship is linear. So either way, it's not a big problem. But when the problem becomes more complicated, or if you do not have the full probability distribution but only the expectation, this method works much better. And this could be the only possible way to calculate the expected value. So that's another reason why understanding this is important. Okay. So next, I am going to tweak the problem a little. So think about a similar but another scenario. So on eBay, I found that someone is selling Disney World ticket. Admission is free, but I have to buy that $700 right now. I need to decide it right now. So I can use this ticket for the next year, from like within a year from now on. And then I need to think about whether this deal is worth or not, right? So original price was $1,000. Original admission was $1,000, but somehow I could get it $700. But the problem here is I need to buy it right now if I'm to buy it. But I may not go to Disney World. So it's discounted, but the risk is I'm not using it, right? So then we will think about the problem using probability distribution again. So the scenario goes like this. I have to pay $700 if I take this deal. I have to pay $700 even if I don't use the ticket, right? I may not use the ticket at all. And if I go to Disney World twice, then the second trip should be regular price. So it is just only one ticket, right? So the distribution, like the new random variable z, I'm going to define a new random variable z as the total spending on Disney World if I buy this ticket from eBay, right? If I decide to buy this ticket, then the new random variable looks like this. So if I do not go to Disney World next year, still I spent $700 on eBay, basically for nothing, right? So 50% I spent $700. If I go to Disney World once, then the ticket I bought on eBay, it's sufficient. So $700 will bring me into the Disney World. So $700 is my spending, final spending, 40%. But when I go to Disney World second time, then I have to pay regular price $1,000. So total will be $1,700 with 10%. Now you try this. Calculate the expected spending when I take this deal on eBay. So this could be a little bit more tricky, or it's up to you. So try this and find your answer. Okay, so let me solve this problem. The answer here is, the trick here is to Travis, that this problem is not linear, right? So that's the first thing you need to realize. So this is not linear because a simple way to tell that is, so when it is linear, you should be able to express the relationship as original variable times something plus something. But in this case, that's not allowed because when x changes, the increment is not constant. When x changes from 0 to 1, z does not change. But when it changes from 1 to 2, x changes from 1 to 2, z increases by 1,000. So the increment is not the same. That means when you think about graph, like slope is different. First slope is 0 and then 1,000. So it is not linear. For a function to be linear, the slope should be the same. So this is not that case. Therefore, it's not linear. So what I'm telling you here is, it is actually easier to see that something is linear because you can write that as a linear function. But what is more difficult is to tell it is not linear, because mathematically showing that it does not satisfy a certain condition is more difficult, because you think there is no linear relationship, but if there is at least one way to do that, then that breaks your conjecture. So like when you can write down as a linear function, that's clear. That clears the answer. But when you cannot write the relationship as a linear function, then either it could be really nonlinear, or it could be just because you could not find a way how to write it as a linear function. So this is more difficult problem. And here is one simple rationale, like check if the slope is constant or not. And then in this case, the slope changes, which means it's not linear. Anyhow, as a result, we cannot apply the linear relationship formula. Therefore, there is no other way. Just do it the basic way. So multiply z with probability and calculate probability weighted outcomes and write them down here. Sum all the probability weighted outcomes, and the answer is $800 in the end. That's interesting, right? So in the end, compared with the previous expected value, if you just pay regular price, the expected spending was $600. But now, if you buy a discounted ticket from eBay, your expected spending increased. You are spending actually more. So it's more expensive. That means it is not a good idea to buy the ticket, discount ticket, because you may not use it. And that probability is pretty large. 50%, you are going to lose it. So based on the expectation, your decision is the right decision is not to take the deal on eBay. Okay, here is another scenario. I don't know if there is anything like this, but just assume that. Suppose that there is an annual membership, like premium annual membership, right, for Disney World. So that is like the annual fee is $600 to join the membership first upfront, and then when like for a year you become a premium membership, and if you are a member, then you can get a ticket for $500. So you get discounts, right? But you have to pay upfront fee, and what I'm saying here is, first thing is similar. You need to decide whether to buy the membership right now. It is like, say, limited time decision. You need to make it today, to make the decision today. And once you buy the membership, then it is valid for a year. And no matter how many times you go to Disney World, you get the discounted price, right? So that is the assumption, the scenario in this case. So now then I will think about the problem if this membership is worth. That's another interesting question. So I will define random variable W is the total spending, random variable, total spending if you decide to join the annual membership. If you decide to pay the annual fee right now, and then what would be your expected spending, right? Economically, the idea is similar. The problem is, even if you you become a premium member, still the problem is you are not going to use it with 50%, right? So if you pay the annual fee, but if you do not go to Disney World, you are just losing it, right? That's the risk. Then, is it worth to take this risk or not? Okay, here is the new probability distribution table. It's clear. So even if you do not go to Disney World next year, still you already paid the annual fee, $600. But if you go to Disney World once, you only pay additional $500. For the second trip, another additional $500. And the probability is the same. So these are the spendings for each scenario, right? For each number of trips. Then now another exercise. What is the expected value of W, the spending, if you use this membership? And of course, what you need to think about first is to check, think about if this relationship is linear or not. If linear, the problem becomes pretty easy. If not, need some algebra. Okay. So the answer is the relationship is linear because, so it can be written in this way. W, if you use the annual membership, your cost is like this. Go back to this table. So what you can tell here is from 0 to 1, when X increases from 0 to 1, W increases by 500. When X increases from 1 to 2, W increases by 500. So the slope is the same. In this case, there are only two increments, like from 0 to 1, 1 to 2. So that's enough. All slope is the same for every interval. And then mathematically you can write it this way. So the new random variable, the spending after being a membership, being a member, can be written as upfront fee $600, a fixed cost. $600 is already paid. You already spent $600, which is one-time payment, and it's paid regardless of your number of trips. So 600 is fixed, plus for each trip you pay additional $500, right? So in that sense, it is linear, right? Multiply 500 and add 600. And then because we just verified the linear relationship, you could simply plug in the expected value of the original expectation here. In the place of x, just use its expectation, and then 0.6 is plugged in, and the answer is then you get the expected value of the new random variable, which happens to be 900. And then again, it is higher than $600, which was the expected spending without any discounts, just regular price. So as a result, the right decision is not to buy this membership. So the annual fee is too high, or you are too much likely to not use the membership at all. 50%, you are going to lose the membership fee at all. So far we learned a lot of things in this interesting example. By the way, one more thing. I did not show you this. So in the last problem, still you can use the fundamental way, the safe way, to calculate the mean. The result is the same, just it takes more time, more algebra. So calculate probability weighted outcomes and sum them. That is always true. So if you are not certain about linearity, then I recommend you do this, right? But understanding linearity is pretty useful. Okay, so this is the end of this example, and you learned a lot of interesting things. First, what is linear and what's not, and how we apply the formula for expectation when the relationship is linear. And also, as I said, we are learning expectation to make decisions easier. As you can see, I'm showing you by calculating expectations, you can make the decision whether the like membership or a discount is worth or not. So yeah, this is the end of this video. And in the next video, I'm going to change the topic a little bit. So far, I said only the good things about the expectation. I only said as if like expectation is perfect, omnipotent, but actually not. There are many problems with expectation. So in the next video, I will show you an alternative, and potential problem with using an expectation. Okay, thank you for watching. See you in the next one.